Last time we concluded with our discussion of binding variables. We will now begin our discussion with logical equivalences involving quantifiers. Definition 3. Statements involving predicates and quantifiers are logically equivalent and only if and only if they have the same truth value no matter which predicates are substituted into these statements and which domain of discourses is used for the variables in these propositional functions. We use the notation S is equivalent to T to indicate the two statements S and T involving predicates and quantifiers are logically equivalent. Example 19. Show that for all x, the quantity P of x and Q of x, and for all x, P of x, and for all x, Q of x are logically equivalent, where the same domain is used throughout. Solution. To show that these statements are logically equivalent, we must show that they always take the same truth value no matter what the predicates P and Q are, and no matter which domain of discourse is used. We can show that for all x, P of x, and Q of x, and for all x, P of x, and for all x, Q of x are logically equivalent by doing two things. First, we show that if for all x, the quantity P of x and Q of x is true, then for all x, P of x, and for all x, Q of x is true. Second, we can show the reverse, that if for all x, P of x, and for all x, Q of x is true, then for all x, the quantity P of x and Q of x is true. We'll do the first one first. Assume that for all x, P of x, and Q of x is true. Let A be an element in the domain of discourse. Then P of A and Q of A is true by employing the assumption. P of A and Q of A is true by employing the definition of and. Because P of A is true and Q of A is true for every element in the domain, we conclude that for all x, P of x, and for all x, Q of x are both true. This means that for all x, P of x, and Q of x. Now, the reverse. Assume that for all x, P of x, and for all x, Q of x is true. For all x, P of x is true. For all x, Q of x is true. Let A be an element of the domain of discourse. P of A is true because for all x, P of x is true. Q of A is true because for all x, Q of x is true. For all A, P of A and Q of A is true. It follows that for all x, the quantity P of x and Q of x. We conclude that for all x, P of x and Q of x is equivalent to for all x, P of x and for all x, Q of x. Nesting quantified expressions. Consider the statement, every student in your class has taken a course in calculus. The statement is the universal quantification for all x, P of x, where P of x is the statement x has taken a course in calculus. The negation of the statement is, it is not the case that every student in your class has taken a course in calculus. This is equivalent to, there is a student in your class who has not taken a course in calculus. The foregoing example illustrates the following logical equivalence. The complement of 4x P of x is equivalent to there exists x, the complement of P of x. Table 2 lists the De Morgan laws for quantifiers and when negation is true and when it is false. The negation, the complement of there exists x P of x, is the equivalent statement for all x, the complement of P of x. When is the negation true? For every x, P of x is false. When is it false? There is an x for which P of x is true. Now consider the second row where we find the complement of for all x, P of x. The equivalent statement is there exists x, the complement of P of x. There is an x for which P of x is false. That's when the negation is true. When is it false? When P of x is true for every x. Remark. When the domain of a predicate P of x consists of n elements, where n is a positive integer, the rules for negating quantified statements are exactly the same as De Morgan's laws discussed in section 1.2. This is why these rules are called De Morgan's laws for quantifiers. When the domain has n elements, say x1 through xn, it follows that the complement of 4x for all x p of x is the same as the complement of p of x1 and p of x2 and p of xn, which is the equivalent to, say, the complement of px1 or the complement of px2 or the complement of pxn by De Morgan's law. And this is the same as there exists x, the complement of p of x. Similarly, the complement of there exists p of x is the same as the complement of p of x1 or p of x2 or p of xn, which by De Morgan's laws is equivalent to the complement of p of x1 and the complement of px2 and the complement of pxn, which is the same as for all x, the complement of p of x. Example 20.1. What is the negation of the statement, there is an honest politician? Solution. Let h of x denote x is honest. Then the statement, there is an honest politician, is represented by there exists x, h of x, where the domain consists of all politician. The negation of this statement is the complement of there exists x, h of x, which is equivalent to for all x, the complement of h of x. This negation can be expressed unambiguously in English as every politician is dishonest. Example 21.1. What are the negations of the statements for all x, x squared greater than x, and there exists x, x squared equal to? The solution. The negation of for all x, x squared greater than x is the statement, the complement of for all x, x squared greater than x, which is equivalent to there exists x, the complement of x squared greater than x. This can be rewritten as there exists x where x squared is less than or equal to x. The truth values of these statements depend upon the domain. Example 22. Show that the complement of for all x, the quantity p of x implies q of x, is equivalent to there exists x, the quantity p of x, and the complement of q of x. Solution. We have the expression, the complement of for all x, the quantity p of x implies q of x, which is our origin on the left-hand side of the equivalence operator. That's our initial assumption. Then what we do is we go ahead and apply our definition. We say there exists x, and we complement the p of x implies q of x. And then we take from section 1.2 table 7 row 5 and use the equivalence, the p of x, and change the complement of p of x implies q of x to p of x and not q of x. Then we proceed to prove the other side. And so we take there exists p of x and not q of x, which is our initial assumption. And we transform the p of x and not q of x to not p of x implies q of x from section 1.2, table 7, row 5. And we finally arrive at the complement of for all x implies, for all x, p of x implies q of x. Translating from English into logical expressions. Example 23. Express the statement, every student in this class has studied calculus using the predicates and quantifiers. Solution. First, we rewrite the statement so that we can clearly identify the appropriate quantifiers to use. For every student in the class, that student has studied calculus. Next, we introduce a variable x so that our statement becomes, for every student x in this class, x has studied calculus. We introduced c of x, which is the statement, x has studied calculus. We also confine the domain of discourse to students in the class. Our statement can be expressed for all x, c of x. If we wish to change the domain of discourse to consist of all people, we need to express our statement as for every person x. If the person x is a student in the class, then x has studied calculus. Let s of x represent the statement x is a person in the class. Our statement can be represented as for all x, s of x implies c of x. Caution, our statement cannot be expressed as for all x, the quantity s of x and c of x, because this statement says that all people are students in the class and have studied calculus. I think we'll stop our lecture here, and we'll begin a new lecture that talks about the exercises at the end of the text.